there, and welcome back to the Sea Slug Show. I'm Elise Letts, and this is episode 5. What do sea slugs, photons, and cupcakes have in common? This episode. But before I get into that, I just want to give you a quick update on what's going on. This week is pretty exciting because I'm going back to Spain to collect. So I will report next week from Spain about the collection and let you know how that's all going. Now about those photons and sea slugs and cupcakes. In this episode, I will talk about photosynthesis and how we measure it in living tissues in real time without disturbing those tissues, plant or animal. That's right, some animals can do photosynthesis. If you remember, we've been talking about solar-powered sea slugs the last couple weeks, and that's what I measure photosynthesis in. Acclamation sea slugs, or solar-powered sea slugs, are a group of slugs that steal chloroplasts from their algae food. They steal these chloroplasts and then they keep the chloroplasts inside their bodies for quite a period of time. The chloroplasts keep functioning, keep doing their thing, and we can measure how much photosynthesis they're actually doing, and that's what I'm going to explain today. So when I say that the chloroplasts are still functioning and still working, I mean it. I mean that they are taking carbon dioxide out of the water and transforming it through photosynthesis into oxygen and sugars. Now, we don't know exactly what the benefits for the slugs are, other than a longer lifespan. Which is part of the project. That's actually part of what I'm trying to figure out. The important thing we want to know for today, though, is how much photosynthesis they're doing at any given time. And we don't really want to cut up the animals to figure that out, because, well, you can imagine they don't really like that. To understand how we measure photosynthesis in living tissues, we need to know a little bit about photosynthesis. Now, I'm not going to get into too many details because it's quite a complicated process. If you do want to know more about the entire photosynthesis process, the SciShow did a great episode, and I'll put a link in the description below so you can check that out. What we need to know here is just a little bit about the first step. So we need to know what happens when a photon, or a packet of light, hits a chlorophyll molecule inside the chloroplast. So remember, the chlorophyll sits in the chloroplast. That's the part of the chloroplast that's actually doing the photosynthesis. There are other pigments there, but for today's purposes, that's not what we're interested in. We're really just interested in that chlorophyll and what it's doing for the sea slug. Photosynthesis is comprised of a bunch of different chemical reactions, and they all have to go just right in order to get the products, in order to get the sugar and the oxygen release. These reactions can be grouped into two different cycles, the light-dependent cycles and the light-independent cycles, or dark cycles, or Calvin cycle. We are only going to talk about the first step of the light-dependent reactions today, and then feel free to check out that SciShow if you want to know the rest of the story. When a photon or packet of light strikes a chlorophyll molecule, it excites the chlorophyll. It energizes it. This means one of the chlorophyll's electrons jumps to a higher energy level. Remember that model of an atom from high school? It had these clouds of electrons? Well, when chlorophyll gets excited, one of these lower energy electrons jumps to a higher energy level. The chlorophyll molecule isn't stable anymore, and one of three things is going to happen. The energy can be released as heat, it can be transferred to a nearby molecule that drives the photosynthesis reactions, or it can be re-emitted, bounced back into the environment as a photon with a lower energy level. This re-emission is called fluorescence, and that's actually what we're measuring. When the excited electron jumps back down to a more stable level, it lets go of that extra energy. This energy is released as a photon, but a lower energy photon than the one it initially absorbed. The equation looks like this. The total energy of light we put in, T, equals the amount going into photosynthesis, plus the amount released as heat, plus the amount getting bounced back at us as fluorescence. So it's a pretty simple equation, but before we get into filling it out, we need to know a couple other things. Each molecule of chlorophyll can only absorb one photon at a time. We also need to know that when it's exposed to short bursts of light, very little heat is radiated. So we can say that heat is basically negligible. That means H in our equation is basically 0. And we have to understand this is a model. It's not exact, but it's pretty good because we're going to be using short bursts of light, so we can discount heat. We also have to know that when a sample is deprived of light for a few minutes, every chlorophyll molecule is ready to accept a photon. They've done one of those three things, and they're all ready to go again. We call this dark acclamation, and although it is not required before measuring, it makes the measurements far more accurate. So I always do it. We also need to know that white light, like the light from the sun, has many wavelengths, all bundled together. These different wavelengths have different energies, and some wavelengths, like the dark red wavelengths, do not have enough energy to power photosynthesis. They do have enough energy to get the chlorophyll to fluoresce, though, and this becomes really important when we take our measurements. You'll see. So this is the machine I use to measure photosynthesis. It's called the Pulse Amp Modulation Fluorometer, or PAM. It uses all of the things I've already mentioned to give us a numerical representation of how much photosynthesis each sample can perform. The electronics are enclosed in this plastic casing and include a light source, sensors, and display panel. It's all enclosed because this PAM can be used underwater, when we dive and take measurements in the field. This cable here is fiber optic, which transmits the beams from their source to our samples and gives us some flexibility. 2 different beams of light are needed to measure photosynthesis. The dark red beam allows us to find our specimen in the dark and to measure the fluorescence emitted by dark adapted samples. Remember, the sample is dark adapted to make sure none of the chlorophyll molecules have photons when measured, and to assure that they are all available to receive one. The measurement we take with the red beam represents the total number of chlorophyll molecules that are ready to accept photons, because the red light cannot drive photosynthesis, and heat is negligible when we're only using these short pulses of light, which is all we're using here. This means only fluorescence is left as an option, so every chlorophyll molecule that can accept an electron is sending the signal back to the sensors in the PAM. The other beam of light needed to measure photosynthesis is a bright white beam. This beam flickers on and off really fast, completely saturating all of the chlorophyll molecules and making them unavailable. The PAM then measures any fluorescence coming back to F. Since heat is still considered negligible, the total T from the red beam measurement minus F from the white beam measurement will equal the amount going into photosynthesis. And the reason that works is because the white beam is driving photosynthesis. But of course, not every single chlorophyll molecule is sending its energy into photosynthesis. There are a few that are bouncing things back as fluorescence. So now if we rearrange our equation so that we're solving for P, it'll look like that. And we can see how much photosynthesis is actually going on inside the sample. If we then divide by T, we get a relative value, which we can use to compare between samples. So here it is in action. I put each slug in its own cupcake cup and then cover them for about 15 minutes to acclimatize them to darkness. Then, zap! Oh, it takes about an hour to measure 24 slugs. That's 2 cupcake pans full. So now to give you a few numbers as an example, an Eleusia timida, the main species I'm working with, that has been eating constantly, has a value of about 0.7 to 0.8. That's 70 to 80%. Whereas a slug that has been starving for 2 months might be closer to 0.3 or lower. The photosynthesis value has dropped a lot. Now it's important to know that this doesn't tell us anything about how many chloroplasts are inside the slug. Because it's a relative value, it just tells us how well photosynthesis is working. It doesn't indicate at all how many places, how many chloroplasts, how many chlorophyll molecules are able to do photosynthesis. So that means that even a slug that's been starving for a really long time can have a high PAM value if a couple of the chlorophyll molecules are doing a really good job continuing on their photosynthesis. So that's something we kind of have to keep in mind. In my experiments, I use these values as benchmarks. I use them to see, maybe that slug has been starving for a really long time. How close is it to complete chloroplast shutdown? Or, that slug has been starving for a while. I wonder, how are its chloroplasts doing? How much photosynthesis are they still capable of? I also need to know that a slug is not too far gone, like I let it starve a little too long, to be too unhealthy to use in my experiments. So that is how I measure my animals' photosynthetic activity without disturbing them, and how I assess their health. Thanks for watching. I hope you learned a thing or two. Please leave comments, questions, feel free to subscribe, all of that down below, and I will see you next week from France.